Hi everybody, today we will talk about hydrates. Hydrates are just any substances that contain water, usually in fixed proportions, and when I mean containing water, I mean that water molecules are actually enclosed inside the chemical structure. So for example, salt hydrates occur when water molecules get stuck in between anions and cations. So for example, in this image, we have a salt hydrate for sodium thiosulfate. So the sodiums are most likely the purple circles, and the thiosulfates are most likely these yellow and red circles. And the water molecules are the ones over here where there are two H's indicated by white and one red atom which stands for oxygen. Now these water molecules are kind of stuck in the crystal lattice structure of this sodium thiosulfate crystal. Now in our formula here we see that for every one formula unit of sodium thiosulfate we have 2/3 of H2O. So, in other words, if we scale this up by multiplying each of these by times 3, then we see that for every 3 formula units of sodium thiosulfate, we have 2 water molecules. So, they are in fixed proportions, and that's what I mean by that. So now let's look at the structure of a salt hydrate. This here is copper sulfate pentahydrate as shown here. I will teach you how to name these very soon in the video. But notice how the 4 water molecules, which I will circle here, 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 and here, are attached to the copper by this green line. This green line is called a coordinate covalent bond, or a dative bond, which is when one atom gives both electrons for the bond. So we study single bonds, and we know that single bonds are usually formed when each atom donates 1 electron each. So for example, if 2 H's each have 1 electron, they both will donate 1 electron each to form this bond. On the other hand, these coordinate covalent bonds happen when this oxygen atom donates both electrons in order to create a bond with copper. And this will be discussed in a video about complex ions. And right now we don't have to get into this that much. Just know that a coordinate covalent bond occurs when one atom donates 2 electrons. So now let's talk about the other interactions going on in hydrates. So we notice that there are actually 5 water molecules in copper 2 sulfate. So where's the 5th water? Well, it's actually located right here, and it is bonded to the sulfate via a hydrogen bond. In this video, we will not talk about what a hydrogen bond is, so don't worry about that. Now, what we need to know is the ionic bond, which is not shown, because an ionic bond is basically the attraction between a cation and an anion due to their opposite charges. So because of this, we don't see any bonds, because bonds are only drawn usually when electrons are involved, and since the only thing involved is an attraction, we simply just don't draw ionic bonds. They are more so implied. So I just wrote it there in order to remind you that the cation and anions of a salt are held together by ionic bonds as shown here. So now let's go on to naming hydrates. So in this example that we did before, the name for it is copper 2 sulfate pentahydrate. Now copper 2 sulfate just comes from this part, and we all know how to name that from the previous video, and if you don't, then watch the video about naming ionic compounds. But I'm assuming you do, so the only different part is this part. This part is showing the hydrated form of copper 2 sulfate, and it's showing the water molecules that are attached to the salt. So in order to write it, you basically write a dot, and then you write the number of H2Os that are attached to each formula unit. So in this case, one formula unit of copper 2 sulfate has 5 waters attached, as we just, described in the picture above. So in order to name this, we just write the salt's name, and then we add a blank hydrate. In our case, we had 5 H2Os. So looking at this prefix chart, we use 5, which is penta. So our final name for this salt right here, is copper 2 sulfate pentahydrate. So let's now go over the prefixes. If you have half an H2O for every one formula unit, you call it a hemihydrate. If you have 1, it's mono, 2, di, 3, tri, 4, tetra, and all of these are just the same prefixes that we used for naming covalent compounds. The only one that's new is probably this one half one, but don't expect it to show up that much. So now let's do a few practice problems. So this shown here is cobalt and chloride. So we need to figure out the charges. This is Cl minus, and this is cobalt 2 plus. And how did I know that was 2 plus? Well, this is minus 2, because there are 2 Cl minuses, which means it's minus 1 times 2 to get that. Then we need a positive 2 charge on the cobalt in order to cancel that out to make it 0, since salts are overall electrically neutral. So we know that this is a cobalt 2 plus cation, and this is also a transition metal, since it's not in groups 1, 2, or any of the other groups that we had to memorize. So this is a transition metal, and it could exist in many charges, so we have to use the stock system. So this would be cobalt 2 chloride. Now we have to include the water part, so it's going to be a blank hydrate. So we're going to figure out what that is. So since there are 6 waters per one formula unit of cobalt 2 chloride, then this will be hexa. Now let's try our next one. We see the same cobalt 2 chloride, but there are no water molecules attached. And because of that, we call it anhydrous because it's without water. So this salt would just be named anhydrous cobalt 2 chloride. And I put the anhydrous in front in order to be specific, saying that there are no water molecules attached to this salt. So let's now talk about some special terminology. So hygroscopic just refers to any chemical, such as a salt like cobalt 2 chloride, that spontaneously absorbs water from the air to form hydrates. So if you put an anhydrous salt out in the open, the salt will, absorb water over time, and this applies to many salts, including sodium hydroxide NaOH, which readily absorbs water from the surroundings, which is why sodium hydroxide is hygroscopic. So that's just one example, and not all salts are hygroscopic, but most of them are. So now let's talk about what a methane hydrate is. A methane hydrate is when a methane molecule, which is CH4 if you didn't remember, is when, a methane molecule is trapped in a cage of water molecules that are in their solid state. So in this diagram here, we have a white circle, which is a methane molecule, being enclosed in a crystalline structure made of water. So water, when frozen, turns into ice, and ice is a crystalline solid. So it forms, intricate crystalline structures that are very organized, such as the one over here. And sometimes they are able to trap these methane molecules in them. So that's what a methane hydrate is. So if you burn a methane hydrate, it will spontaneously combust, because think about it. A methane hydrate is just a piece of ice with a bunch of methanes trapped in it. So when you burn a methane hydrate, the methanes inside the ice cage will come out and burn because methane is flammable. So that's why when you burn normal ice, ice doesn't burn because ice is water and water is not combustible. Meanwhile, methane is combustible. So that's something cool to know, that ice can actually burn sometimes. So now let's do one more practice example, or maybe two. So let's try naming this one. This one will be sodium chloride dihydrate. Now this one we have to convert the name into the chemical formula. So sodium hydroxide is NaOH, and monohydrate is just, well, it's just 1H2O, or you could just write H2O and omit the 1 since it's implied. So I just want to talk about one more thing. I wanted to talk about how the hydrated form of salts is sometimes different from the anhydrous form of the salt. So in this example, we have UO3. Now this is a salt, so let's try naming it. So usually what ends up happening is that if you don't belong to the main group element, such as group 1, the alkali metals, or group 2, the alkaline earth metals, then you tend to have multiple charges similar to the transition metals. Just like the transition metals, which don't belong in the main groups, uranium does not belong in any of the main groups either. Uranium is actually an actinide, and it belongs in the period where actinium is. So if you don't belong in the main group elements, then you usually have multiple charges. So since uranium does not exist in any of the main group elements, then uranium will have multiple charges, and things that have multiple charges will theoretically have a name based on the stock system. So in this case, since oxide, or O2 minus, has a -2 charge, then the oxygens will produce a -6, and we need to balance that out. So uranium will have, oops, I skipped to another slide, sorry. Uranium will have a +6 charge. So this salt will be called uranium 6, so 6 is Vi, oxide. And if you want to add the 2 H2Os, then it would be called dihydrate. So as you can see, the hydrated form of uranium 6 oxide and the anhydrous form of uranium 6 oxide are different. And they are different because while one is light yellow, the other one is, I guess, kind of orange, and they also have different properties too. So by adding water molecules into the crystal lattice, you are potentially changing both the physical properties, such as the color, and even the chemical properties as well. You never know. So by adding water to the salt, you are potentially changing the properties of it. So just keep that in mind. And now let's talk about converting from one form to the other. In order to convert the hydrated form to the anhydrous form, we typically heat it up using fire, for example. So if you put the salt under fire, then it will convert into its anhydrous form because the water molecules will evaporate essentially from the crystal lattice. Now, what if we want to convert the anhydrous form to the hydrated form? Well, you can either leave it out in the open for, water molecules in the air to enter the salt, or you could just put some water on it and it will become hydrated. So that's all for this video. Have a wonderful day.